but when the state comes out, this is exactly what they're going to be looking for. This is right out of their radioactive material license. So on page 8 of that handout, okay. So the thing we talked about, okay, acquire 1 million counts for a small field of view camera, 3 million for large field of view cameras. Process the image as if it was a patient study. Look for areas of non-uniformity and collimator damage. Health physicists recommend 3 million counts for small circular field cameras and 5 million for rectangular cameras. For computer analysis floods, use 10 million to 15 million counts. Okay. If the camera has uniformity correction, then acquire an image with and without the correction on a weekly basis. Now, some people do it daily. Okay? But remember that the uniformity should not exceed 10%. Okay, then another recommended step is to do a background activity check with collimator off or on. Remember I said your gamma camera is very sensitive, and so if you take that collimator off and you just acquire maybe a 5-minute acquisition, have it stop after 5 minutes, you'll see if there's any radiation contamination around your department. Okay? The linearity and resolution, we said that was a weekly thing. It says use a 4-quadrant phantom, collect 3 to 5 million counts using the finest matrix available. I don't know if you guys do this or not, but if you do 512 by 512 for doing your resolution floods. The full width half max for the image is approximately 1.8 times the minimum resolvable spacing. Okay, so what this means is you look at the smallest lead strip that you have, multiply it by 1.8, and that's your resolution. Okay, take a tape measure or a ruler, measure those little lead strips in there, or if you kept the paperwork that they sent to you with that, it will tell you what the smallest lead strip is. And that will tell you, okay, so like I said here, so for example, if you see the 2 millimeter bars on the 4-quadrant phantom, the 2 millimeter ones are the pretty small ones. Okay? So your resolution should be 3.6 millimeters. So 2 millimeters times 1.8, that's your resolution. Okay? Then the 4-quadrant phantom requires 4 images to be taken. So you have to rotate after each image. It says linearity requires checking the straightness of the lines of the phantom. So that's a pretty obvious one there. The other thing that I strongly recommend, and this one is ignored by most people, periodically check your whole body mode using the transmission phantom. So basically what you're going to do is you're going to put your cobalt source on your bed, put the linearity or put your transmission phantom on that, or put your bar phantom on that, and you scan it as if it was a whole body. Okay? And then just look at it. Because a lot of people don't. They, like I said, if you really want to impress people and it's a slow day, say, hey, why don't we do let's check and see how well our whole body mode is. And so you're just going to put your source down there, you're going to scan your transmission phantom, and then you're on your way. This next one that we're going to be talking about here is sensitivity. This is also on page 1.
Before you move on, what would doing the whole body mode, what would that even tell you?
Well, it would tell you how well your gamma camera is able to put the whole body back together. Because when you do a whole body image, you're taking little small sections and just sort of stitching them together. And sometimes, like I said, it's you have problems with it. So you may be not aligned properly, or it may be just any kind of problems. Ideally you would do one for like the head area, and then you would move it down to the body area, and then down to the lower extremities. Just to make sure that the whole thing is good. This next one here, okay, on page 136 of your math book, okay, normally when you're doing your floods, you can also do a sensitivity test. It says maybe done with a point source, or if you're using a cobalt source, then what you're going to have to do with the cobalt source is calculate how much activity there is in it. So on your your printout sheet that they sent to you with your Cobalt source, it should tell you what the daily activity is, as it decays down every day. Because what you're going to need for this is the counts per second per microcurie. So, then here it is in the math book. Okay. So it says tracking the camera sensitivity is a useful way of detecting subtle changes in the instrument performance. Day-to-day or week-to-week comparisons allow early detection of potential problems. This allows for preventative maintenance as opposed to emergency repairs. Okay? So basically, a known amount of activity is required. The counting geometry must be identical. So that's especially important if you're doing a intrinsic flood. Okay? It says counts per minute per microcurie, or it can either be counts per second or counts per minute. So basically what's going to happen then is every week you should get about the same number of counts per second. So for example here it said, okay, you had 657 counts per minute with 150 microcurie source. The background was 340. So 26,000 minus the background divided by the number of counts. So there's your counts per minute per microcurie. Okay. Now, I normally did counts per second, but so what you're going to do every week . Here's your source, and then here's your bed. Now, what some people do is, they'll acquire their source. Let's say you get 3 million counts. And it takes 5 minutes to do the flood. And your source here is, let's say, 500 microcuries. Okay. Now, if you remember, the source that we normally use for doing floods is typically about 5 millicuries. And over time, it decays. So when I bought my flood in February 14th of 2012, it was 5 millicuries, and that means each day. So the 15th it'll be 4.9 or something millicuries, and then the 16th. So in other words, it's going to decay. So let's say that by December it's down to 4.1 millicuries. Okay, you can still do your daily floods. Let's say I go for 3 million counts in 5 minutes. So how many counts? That's 600,000 counts per minute. And we had background. Let's say the background was 10,000 counts. So, and then we had 500 microcuries here. Now remember, if I was using millicuries, I would have to convert that to microcuries, wouldn't I? So 5 millicuries would be how many microcuries?
5 millicuries?
Yeah.
1,000?
Okay, so it'd be 5,000 microcuries. Okay, because normally it's expressed in either counts per minute or counts per second per microcurie. So that means you have to break that down. Okay, so we've got 5,900 counts with 500 microcuries. So roughly about 5 into 5,900. So roughly about 2,450 counts per minute per microcurie. Once you've calculated that, then that number should stay fairly consistent every week that you do your consistency test. Even when you get down to December or 1 or 2 years from now. Obviously it's going to take longer to do the test every day, but that's why I said a lot of people just do the sensitivity test when they're doing their uniformity. So that way you're kind of killing two birds with one stone. Does that make sense to everybody? Because you know you're going to see it on a quiz that I give you, right? Normally when you do these calculations, though, you're going to get something like this. You know, you'll get about 173 counts per minute per microcurie, so it's usually fairly low numbers. And again, what your expectations are that this number should be the same every week. Okay, should be within this ballpark. Okay. Trying to think what else they have.
To get the background, you just let it run with no sources in order for how long?
Well, let's say, I mean, you can do it for however long you want. Normally, if you just do it for a minute, like I said, you can count your source for a minute. But if you remember, the longer you count it, the more accurate it's going to be. So if you go for 5 minutes, or however long it takes, you know, like I said, when people do their flood source uniformity images, you can just let it go and you tell the thing shut off at 5 million counts. Okay, so you do your 5 million counts, just record how long it takes, calculate how much activity there is in your source, and you can do the sensitivity from that information.
Oh, so you don't need the background?
Well, I mean, then you take the source away and put it away, and then you do a background count for 5 minutes.
So it must be the same length of time that you counted the source.
Yeah, you know, basically one of the things that we didn't talk about in the statistics section was, well, we talked a little bit about it, the effect of background on counting rates. In your math book on page 53, you know, count rates, so the number of counts divided by the time, okay? And then there's another thing here, effect of background on counting rates, okay? And again, we have the net counts is equal to the gross counts minus the background. But what we didn't talk about, well, okay, so this is kind of simple here. So here they counted the cesium source for 3 minutes. They did a background count for 3 minutes. They divided them. You know, they added the total number of counts minus the total number of background counts divided by 3 minutes. So this is another way of doing it that's, you know, more accurate. Like I said, the longer you do it, kind of averages things together. Okay. Now, so I mean, ideally it would be nice to count for the same amount of time, but that may not happen. One of the other things that we didn't talk about was the standard deviation of the count rate. Because you remember when we said that if you did separate 1 minute counts, okay, you're going to have different numbers, right? So you have, let me see if I can find it here. On page 76, take a quick look at that for a minute. Standard deviation of the count rates. because what doesn't make sense sometimes is how we do this thing. Okay, if you take a look at this down here, okay, it says what is the standard deviation at 68% for the sample that produced 5,240 counts in 2 minutes? Okay, well you notice that we took the total number of counts, we divided it by the amount of time that it was recorded for. We get 2,620 counts. And so then in order to calculate the standard deviation of the count rate, we take the number of counts per minute, we divide it by the number of counts it was observed for, and then we get the square root of that, which is equal to 36. So what they're saying is your actual count rate is 2,620 plus or minus 36. Okay. So we do this for the net counts, we do this for the background counts. So you can have different counting rates, but you have to take into account that every minute you're going to have fluctuations of your counts. Trying to think of where the... Is everyone kind of okay on that? So, if you... let's say that you got 50,000 counts in 10 minutes. That's your gross counts. And you got 3,000 counts in 10 minutes for background. Okay, then in order to calculate, okay, first of all, you get your counts per minute. So this would be 5,000 counts per minute minus 300 counts per minute. Is that
5,000 or 50,000?
50,000?
And on the bottom?
3,000 counts in 10 minutes.
But you divide for 10 also.
So then I divided it by 10 minutes to get the counts per minute. Okay. So our net counts is 4,700 counts per minute. Okay, but now we have to take into account the standard deviation. Okay. So this would be then plus or minus, and then this is going to be the square root of 5,000 counts per minute divided by 10 minutes plus 300 counts per minute divided by 10 minutes. So the statistical count rate would then be 4,700 plus or minus the square root of 500 plus 30, so the square root of 530. So what they're saying is, okay, 4,700 and then whatever this is here, square root of 500 is what?
About 23. Oh, sorry. Square root of 500 square root is about 23.
Okay, about 23? Okay. So what they're saying is, okay, during this 10 minutes that you're counting, we all know that you're going to get different count rates. So you might get 4,723 in the first minute, and then 4,677 in the second minute. So the count rate is fluctuating every minute. But so what you're actually looking at here is just the average. Okay. But you also need to calculate, okay, what would be the predicted fluctuation per minute as you're counting. Okay. Now remember, this is for one standard deviation. So if I'd asked for 2 standard deviations of this count rate, then what would it be?
Plus or minus 46.
Be plus or minus 46. Yeah, whatever the standard deviation is here, you're just going to multiply it by 2. Okay, so that would be 46. So that, I mean, but that's something that's related more to the statistics thing what we're concerned with though is, okay, coming back to our quality control here. Okay, so the sensitivity, the counts per second per microcurie, on a board exam question, since most people use a cobalt source, they're going to be decaying down to cobalt. So if you have a 5 millicurie source on 2/15/2012, and you're going to do a sensitivity test on 12/15/2012. Okay, what are you going to have to do to figure this one out? And we're going to go for 5 million counts.
Figure out the decay.
Okay, so we're going to have to figure out the decay factor. So what would the decay factor be?
603 divided by 271 days.
Okay, and let's go through with this. Just like I say, people like me put questions like this on the board exams. So, okay, so 0.693 divided by 271. Okay, so it's equal to 0.0025 per day. Okay, so we would then how many days are there between here and there? Let's just say that there's 30 days in every month. So let's say 10 months times 30 days, 300 days roughly. Okay. So 5 millicuries times e to the minus 0.0025 times 300. Okay. And what do you guys get? About 47%. Okay, so 5 millicuries times 0.47. You could probably at this point make this 5 millicuries into microcuries. So 5,000 microcuries times 0.47, you now actually have 2,361 microcuries 300 days later. Okay. So we would expect then, if it took, let's just say it took 3 minutes to acquire this. So the sensitivity for this then would be, what would my sensitivity be? Okay, 5,000 counts in 3 minutes is how many counts per minute? got 5,000 microcuries, and we have, we have 5 million counts. And 3 minutes. So that's roughly what? Okay, so we've got about
1.7 times 10 to the 6.
yeah, 1,700,000. No, wait a minute. That should be 0,000. She's got 1 million. Okay, 1,700,000 counts per minute. Okay, so 1,700,000 counts per minute divided by 5,000 microcuries would tell us what our sensitivity is. So it's about 340 counts per minute as of that date. Now, if I asked you for counts per second, then you would divide that by 60 seconds, right? Okay, so that's for 2/15/2012. Now, let's say we go to December, and we've been doing weekly sensitivity tests. We should be getting that same number all the way through. So let's say that December 12th. Okay, we still go for our 5 million counts, but now it takes 6.38 minutes to acquire it. What's our activity going to be at that point? What did we say, 2,600 and something?
361.
How much?
2361.
Okay, so now this is decayed down to 2361 microcuries on 12/12/2012. So that's 300 days later, correct? So what's our sensitivity now?
A little over double. Or half.
Well,
It takes twice as long.
it's taking twice as long to acquire. Remember that radio, the number of counts that you take is directly proportional to the activity. So if my activity has decayed by 47%, that means it's going to take 47% longer. Yeah. So in this case here, I should have the same counts per minute per microcure. Okay, I still should have somewhere, 5 million divided by 6.3 minutes. So 5,000,000 divided by 6.38.
How'd you get 6.38 again?
I just took the original time that we had up here and divided it by 0.47, or multiplied it times 47%. So it should be the same number. Calculation wrong.
3 minutes divided by 0.47.
How much?
3 minutes divided by 0.47 gives you 6.38 minutes.
Yeah. What it's saying is that if your activity decayed by 47%, then it should take 47% longer to do the study. So if you do the calculations here, you should still get 340 counts per minute. Hopefully you did. So 5 million Okay, divided by 6.38. Okay, that's 783,699 counts per minute. Seven eight three. Okay, and then you divide that by 2361.
332 counts per minute.
What is it?
I got 332 counts per minute.
Okay, yeah, about 331 counts per minute or 332 counts per minute. Okay, if you carried that out to all of the proper decimals, you should have gotten 340 again. Okay, if we would have carried it to so many number of points. But that's what sensitivity is trying to show you, is that you shouldn't have variations of the counts per second per microcurie over time. Is it hot in here or is it just me? Are you guys getting hot? I'm having menopause. Yes. Okay. Now, this other thing down here, okay, multiple energy spatial resolution. What in the world is that? It sounds pretty cool, doesn't it? Whatever it is. But what is it? Okay. Multiple, says, notice, take images of multiple energy radionuclides, 67 gallium, indium, or a 2,1 thallium, with each energy and without moving the source. Each image should be exactly superimposed. Okay. This is when I was kind of playing around. Each window. First of all, over here, I was doing some off-peak stuff. This was a long time ago, as you can tell. But you notice over here, there's kind of like one image here, and then there's like another one on the outside. When you have two different energy radionuclides, they should be X and Y positioned in the same area, correct? In other words, let me just do this. Okay, okay, here's our gamma camera. And here's my imaging bed. Okay, and if I put a source of, let's say, indium here, 111 indium, okay, what are the energy windows?
247.
And when I'm imaging indium, I should be using both of those, right? Because it makes the image go faster. Okay, so if everything is working properly, now each one of these has its own X and Y positional signal. Each one of these has its own Z pulse. So there's actually 3 pulse height analyzers, 3 XY positional things. So just, take that picture that I showed you, multiply it times 3, as far as, doing the same thing for other windows. So if I take a picture of the 173, I ought to have a dot right in the center there, correct? If I turn this one off and I turn this one on, then I should have a dot in the same spot, unless my source moved on me. Agree? But if I have a dot outside over here, okay, what does that tell you? No, the source didn't move. Assuming your source didn't move, then what would be the other explanation? Well, remember we have X and Y amplifiers and we have Z pulse things. Okay, normally these things should be superimposed on each other because the source is here, the source hasn't moved. When I see 2 separate dots, or I see something that looks like this, a ring around the dot, okay, that means that one of my pulse height analyzers, or not my pulse height analyzers, but one of my X and Y amplifiers is off. It's not recording this thing in the exact position that it should be. With me on that? So multiple energy registration is designed to identify problems with pulse height analyzers on multi-peak radionuclides. That's what we would use it for. And what you saw in that picture that I just had up there, this one's probably a little bit, you see that there's one that's centered here, and then there's another one behind it. Okay? So I've got two different peaks that are not centered on each other. Okay?
Are used to determine problems with what equipment?
Basically, if you are using more than one window, okay, most gamma cameras allow you to image 3 peaks for like gallium. Or if you're doing a study, like let's say you're doing a combination gastric emptying with technetium sulfur colloid and indium DTPA. Okay, let's say you're doing a liquid solid study. Okay, what you would do is you give the patient the sulfur colloid for the solid meal. You'd be imaging on one window with technetium. Then you give them a liquid with indium DTPA, and then you're imaging that for the liquid part. Okay, so you're able to look at the emptying of both solid and liquid at the same time, rather than doing one and then having to do the other later. You do both together. Or if you're doing gallium, you know, you do the 93, 184, and 296 windows to take pictures with. But, as I said, if the source hasn't moved, then all of those peaks should put the X and Y information in the same part of the picture, right? You should not have 3 separate dots if I'm using 3 peaks. Or in this case here, I don't know, can you guys see that? Okay, there's like another window on the outside of it. So that's telling me that one of my X and Y amplifiers is off, and it's not putting the dot exactly where it should be. Okay? What some people do is they'll take a picture with the 173 window, and they'll take another picture with the one with the 247 window, and then they'll take one with them both together. And then they'll superimpose, they'll just stack them on top of each other and make sure that they're all in the same spot. So does that make sense to everybody? Ashley, Mr. Singh? That make sense? Okay. So that's called multiple window registration, and it's only used for radionuclides that have more than one photopeak. Okay? Then, the other thing that we have here, okay, I don't know if you ever bother to check your emergency locks, emitter locks. Oops. Okay, you know all those red buttons that you have that are supposed to turn off the machine in case the patient's arm gets caught? They just had a horrible accident in radiation therapy where the therapy machine knocked the patient off the table. Nobody was able to get over there and stop it because they didn't know what to hit or what button to push. The patient was very badly injured. Broken hip, broken humerus. Yeah. Yeah, massive lawsuit. And that just happened recently. So, thank God it was in radiation therapy and not somewhere else. But that's why you have to be familiar with your equipment. When you guys get in there, what do these buttons do? Okay, so on this thing here, the interlocks and emergency switches, you know, make sure they're working properly. If it really totally disrupts your whole system, then I wouldn't suggest doing it, but just know what it's supposed to be there. The motion switches, and the thing that I'm talking about here is, you know, your whole body imaging, make sure that it's not jerky, make sure that it rotates around properly, make sure that the numbers that it's recording are accurate, check the angulation of your detector, okay, there should be a bubble level on your detector to make sure that it's level. That's especially important if you're doing any kind of spec images. Okay? And then lastly, now this is just routine quality control for most of your, just a gamma camera. The 3 years is how long you need to keep your records. Okay? On that happy note, why don't we call it for, well, we're going to start spec quality control next. I'm trying to think if there's